representing such integers, and that is connected to the special value L1 chi for the quadratic characters. So in particular for quadratic characters mod p, I've given you a formula there. And maybe even not so long after Gauss, we have the class number formula from Dirichlet, which connects L1 chi with, let's say, class numbers of quadratic fields, or in the case of real quadratic fields, also with the regulator added. And already these connections make you wonder about the distribution of values of the number of ways of writing integers as sums of 3 squares, or equivalently of L1 chi d. And there are two kinds of problems that you could ask. One is, what happens for a typical character? What do these values largely look like? And then, of course, the very interesting problem of what happens for all characters. So can you give a bound that works for every single discriminant? And these problems have different flavors. So the problem of getting bounds for every single character is certainly a very, very important and difficult problem. We only have Siegel's theorem that is bounded below by d to the minus epsilon. We would certainly like to say much more than that. And we heard from Hugh's talk that, in fact, wanting to say more about this particular problem is, in fact, the genesis of everything we're talking about in this conference. And if we know the Riemann hypothesis, we can certainly do better in this problem of getting bounds on L1 chi. We can get essentially the right order of magnitude, that it grows like at least 1 over log d. But if you ask about the statistical problem of values of L1 chi, that's a much easier problem and much better understood. And you could say that L1 chi d is basically a constant. It's basically 1. It lies between 1/10 and 10, essentially for any value of an L function that you're likely to see. And there's a long history of people working on this. The upshot is that there's a very simple probabilistic model that explains how these values are distributed. So L1 chi d is given by an Euler product, where the Euler product involves chi of p as you range over all the primes p. And the values chi of p take this values plus minus 1. And you can roughly think that it takes values plus minus 1 with equal probability. This is not strictly speaking correct, because I should also allow for the possibility that sometimes the discriminant might have a prime factor p, in which case I should adjust it by making it 0 there. But let's just pretend it's plus minus 1 with equal probability. Then if you take random variables xp independently with probability with values plus minus 1 with equal probability, this product converges almost surely, and you can compute anything you want about this product. So if you want to think of a toy problem of how this distribution looks, just imagine that you have random variables that are coin tosses plus minus 1 with equal probability, and look at the sum xn divided by n and ask for its distribution. If you take the sum of just xn, that's the central limit theorem. But if you weight it down by n, the sum almost converges, so it behaves quite differently from the central limit theorem. What happens for x1 is much, much more important than what happens for x100. So you can study this distribution. The distribution for L1 chi d is not a million miles away from this. They're kind of quite closely related. The one difference for L1 chi d is that the random variables are also multiplicative. So if you look at the decay of tails of finding large values of L1 chi, it decreases like doubly exponentially, like e to the minus e to the tau. So it's not like a Gaussian at all. And this also means that finding large values or finding small values of L1 chi d is extremely unlikely. And that's why I say that it looks mostly between 0.1 and 10. So it'd be pretty impossible to find a value of L1 chi d bigger than 10. And the probabilistic model we expect captures basically all the features that we would like of L1 chi d, even though we can't establish all of it. We would think that you can approximate L1 chi d by taking an Euler product going up to log d, and up to log d, the primes can do essentially anything they want. So this is basically a random Euler product at this stage. we can't quite solve this problem completely. Even on GRH, you can only say that L1 chi d is approximated by an Euler product going up to log d squared. So there's a little bit of lack of knowledge, even in this situation, from what we can say from GRH and what we might think might be the truth probabilistically. But you could say that we have a pretty good understanding of this problem. If you ask for similar questions about the zeta function, so you have pretty much the same picture if you are working away from the half line. So if you take zeta of sigma plus IT and sigma is fixed bigger than half, and you want to understand statistically how this behaves as t varies, then the zeta function behaves roughly the same as a random Euler product, where these random variables xp now are uniform on the unit circle. Again, the product converges almost surely, and you can say anything you want about its distribution. Now, again, we can't really say that the zeta function always behaves like this, because that would again encode the Lindelof hypothesis, for instance. But statistically, this is the answer. Another way of saying what this model is telling you is that there's almost periodicity in the values of the zeta function. So if you can find a value tau such that 2 to the I tau, 3 to the I tau, 5 to the I tau, and so on, up to some number of primes, they're all close to 1, then zeta of sigma plus IT will kind of look the same as zeta of sigma plus IT plus I tau. So whatever behavior you have will kind of repeat with this period tau. This won't be true for all values of t, but it'll be true for most values of t. And you can have the same property for sums of 3 squares. So for example, there's an unexpected periodicity in the number of ways of writing integers as sums of 3 squares. If you take two integers m and n that differ by 8 times, 3 times, 5 times, 7, and so on for the first few primes, then it's very likely that the number of ways of writing one integer as a sum of 3 squares is closely related to the number of ways of writing another integer as a sum of 3 squares. Which is not immediately obvious, but that's what you get from almost periodicity for these L functions. Something different happens if we go to the half line. If you take the Euler product, in this case, 1 minus xp over root p, it no longer converges almost surely. And in fact, you should expect it to diverge almost surely. And instead, what we have is that there is a unique distribution that they all tend to a Gaussian. And this is a beautiful theorem of Selberg from the 40s. And Selberg showed that if you take log of zeta half plus IT, it has a distribution like a complex Gaussian with mean 0 and variance log t. So if you pick any box that you like in the complex plane, and if you take log zeta half plus IT and normalize it, then the chance that it lies in this box behaves like the integral of the Gaussian over that box. And the complex Gaussian is what I've described there. Okay. The idea in Selberg theorem is that if you take log of zeta half plus IT, it doesn't make sense to write it as a sum over primes, but let's pretend that this makes sense. It's not a convergent sum. And let's not worry about what x is. Think of it as some small power of t. Doesn't matter what power of t. It still behaves largely like this. And the different primes p will behave like independent random variables. So it begins to look like a sum of independent random variables. And because the variance is the sum of the squares 1 over p, because this variance grows, that's why you get a Gaussian distribution here, unlike the other cases where the variance doesn't grow and you don't get you get whatever crazy distribution that they have. Complex Gaussian also simply means that if you take the real part and the imaginary part, those are both Gaussians and they're both independent of each other. And the variance is half the variance of the total. So I've again just written down what it means to be a Gaussian. And what Selberg's theorem tells you is that I said that L1 chi looks like it's either between 0.1 and 10. Zeta of half plus IT is a bit different. It's either big or it's small. It's big 50% of the time and it's small 50% of the time. And it never takes constant values for any positive proportion of the time. So you can see this simply by taking, if you take lambda to be epsilon, you can see the values bigger than epsilon times e to the root log t are roughly half. And then if you take lambda to be minus epsilon, go from minus infinity to minus epsilon, you get the other half that I've written there. So there's a very nice problem raised by Ramachandra on this. If you take simply the values of zeta half plus IT, do you get close to every complex number? And this is still an open problem. I think if you knew things about the moments of the zeta function, imaginary moments of the zeta function, then you would be able to make this precise, which was, I think, made precise by Kowalski and Nick-Ekbali. This is in contrast to a theorem away from the half-line, which is this so-called universality theorem, which says that if you take a small circle around 3/4 plus IT, so you can basically get anywhere except near the half-line, so I make this radius less than 1/4, then you can make the zeta function around 3/4 plus IT look like any other function that you want, so long as the function that you're trying to mimic doesn't get to 0. If it gets to 0, you're going to have a hard time because the Riemann hypothesis tells you that presumably zeta of 3/4 plus IT is not going to be near 0, for example. So that's a difference between these two examples. And what I've been speaking about is the typical size of zeta half plus IT. And the next question you could ask is, what about slightly larger values of zeta half plus IT? How big can they be? Or even about what the extreme size of values of zeta half plus IT can be. The next range of values is actually what's captured by this problem of the moments of the zeta function. It's a classical problem going back to Hardy and Littlewood. You can imagine that if you let k go to infinity, then you're capturing the L infinity norm of the zeta function. And each moment is capturing values of a certain size, as we will see. So there are only two cases in which we know, well, I guess you could take k equals 0 as well. So, but two positive values of k for which we can compute these moments asymptotically. And these are both about 100 years old. You can compute the second and the fourth moment. And if we could compute as many moments as we can, we would get the Lindelof hypothesis. But even if you could compute just the sixth moment, you would be able to get some results on primes or the density of zeros of the zeta function out of that. So we heard this briefly mentioned in the talks in the morning, that there's a conjecture for how the kth moment should grow. And it should grow like t log t to the k squared times some constants. And roughly it should be grow on the scale of t log t to the k squared. I think it's like a folklore conjecture. But this idea that it should grow with these particular constants, ak and gk, even though it wasn't clear what gk should be, I think first goes back to Conry and Gauche. And Conry, Gauche, and Gonek in the 90s, they realized that, okay, so these two results are Hardy and Littlewood and Ingham, and Conry and Gauche came up with a conjecture for the sixth moment that this constant should be 42. And then Conry and Gonek came up with a conjecture that G4 should be 24,024. And we're not able to guess what the larger values of GK should be until in 98, you had these conjectures of Keating and Snaith. Again, we heard a bit about this in the morning. So this is GK. It looks like an easy number at the end of the day. So somebody could have guessed it, I suppose, but not so easy to guess from just these 4 data points. Oh, so this is, let's take x of p again, like this random model, take it to be uniform on the unit circle and take the, so this could have been like a model for zeta of half plus IT, except it doesn't converge. But you can take all of those and multiply it by its kind of expected value, and you get a convergent product. And that's what the arithmetic factor AK is. I'll say again what AK is from a slightly different point of view. So why should the moments of zeta function have this order of magnitude? This is answering Alex's question again. If you formally write out the kth power of the zeta function, it looks like the k divisor function dkn over n to the s. So you can imagine that maybe some partial sum of this is some kind of good approximation to zeta of s to the k. It's not true, but we can pretend. And then I can try to compute the L2 norm of some partial sum. So here, the main technique we are using is that if you have a short Dirichlet polynomial, you can compute its L2 norm. You just expand it out. So you have am, an, and then you have an m over n to the it. So you get the Fourier transform of this function phi. And the Fourier transform will decrease rapidly. Imagine it's a smooth, nice, smooth function. So it will decrease rapidly as you move away from 0. So only the terms m equal n will matter, where this will be phi hat of 0. For everything else, if n is smaller than t, what you're putting into the Fourier transform here will be something that's growing, and you can neglect all of those terms by just the decay of the Fourier transform. So in other words, this is an example of a large sieve inequality. So for example, we'll hear more about large sieve inequalities in general in Matt's talk in an hour. So what it means is that if n is reasonably small, you can approximate this L2 norm by just the diagonal terms, so the sum of the squares of the divisor function over n. It's a simple matter to find asymptotics for that. And if you work that out, you get this same constant AK times the right power of log t to the k squared over k squared factorial. So in other words, this AK log t to the k squared over k squared factorial would be what you should think of as the obvious guess for what the moments of the zeta function should look like. And the GK are the deviations from this obvious guess. You can actually make this precise for k equals 1 and 2, and that's the theorem of Hardy and Littlewood and Ingham. But for larger values of k, you need to understand things like divisor correlations of understanding the 3 divisor function, for example, d3n times d3n plus 1, which is still an open problem. And there are conjectures for how these divisor correlations look. And then you can try to hope that you can take these conjectures and get guesses for how the higher moments should grow. So this is what was carried out by Conry and Gauche for the 3rd moment, and then by Conry and Gonek for the 4th moment at a heuristic level. We'll hear more about this also, I think, in Zeke's talk, Zeke Baluyut's talk on Thursday. And we heard a little bit about this in John's talk in the morning. This is the work that he and Brian have been doing in trying to understand where the term GK in the moment conjectures come from at the level of these correlations. There's a second way to think about where this order of magnitude comes from. And this is maybe one of the things that I'll focus on in this talk, which is that imagine you just have some normal random variable x with mean mu and variance sigma square. Then what we are computing here are exponential moments, the expected value of e to the tx. And this is a simple calculation. So you just write down literally what it means. This is e to the tx. And then this is the probability of your random variable taking values around size u. Okay. And now you can complete the square here. So if you complete the square, you get this same Gaussian integral with the result of completing the square out front. And this Gaussian integral is just 1. So in other words, it's a simple calculation for what the moments of a Gaussian random variable should look like. The exponential moments of a Gaussian random variable should look like. Now recall Selberg's theorem. It tells you that log of zeta is, mod zeta is normal with mean 0 and variance half log t. So if you just compute what the expected value of the 2kth moment of exponential 2kth moment of zeta should be, you would get 2k quantity squared. So that's a 4k squared divided by this 4, so you get a log t to the k squared out of this. So this tells you something about what the problem on moments is trying to capture. If you look at this Gaussian, it's picking up values of u that are close to mu plus t sigma squared. So the same way, the 2kth moment of zeta is picking out values of zeta of size log t to the k. So these are not the typical values of zeta. They are slightly unusual values of zeta, but not so unusual either, not so big. So if you want to understand the sixth moment of the zeta function, you're only looking at values of size log t cubed. So log t cubed to the 6 is log t to the 18. But the measure of the set on which you take values of size log t cubed, that's 1 over log t to the 9. And that's the log t to the 9 in the moment conjectures. This doesn't, of course, tell you what the arithmetic constant ak and the constant gk are. And we have to kind of figure out where they come from. And that brings us to the theme of this conference, that this is connected to problems in random matrix theory, and in particular to the distribution of zeros of zeta of s. So this is a problem that Hugh already talked about. So you could take the ordinates of the zeros of the zeta function, normalize them so that the spacings between two consecutive ordinates are 1 on average. And then the question is, what is the distribution of these spacings? What's the chance that some consecutive spacing lies at a given interval from alpha to beta? And we saw that the answer for this is surprising, that it is related to this corresponding statistics for the spacings between eigenvalues of large random matrices. So we heard already about the encounter of Dyson and Montgomery, which led to all of this. The idea is that if you take a random matrix from the unitary group, arrange its eigenvalues from theta 1 to theta n so that they lie between 0 and 2 pi, and then ask for the distance between two consecutive neighbors, consecutive angles, and then average that over all elements in the group and let n go to infinity. The distribution that you get is supposed to be the same as the distribution that you get for the normalized spacings between zeros of the zeta function. So it's quite a remarkable conjecture. To get a sense of the difference between random numbers and random eigenvalues, here's a picture from a paper of Eric Rains. So the measure has this factor which likes to make the angles differ from each other. If the angles are very close to each other, the measure is very small. So random matrices like to have all their eigenvalues spaced away from each other. So that's the eigenvalues of a large random matrix. Whereas this one, you can see there are many large gaps, but then there are also many zeros that are clustered together as well for random numbers. It's a bit funny to say that this is a picture of a random matrix and the random 100 random numbers, because it's from a paper from 25 years back. So they're not quite random at this stage. So we already saw this graph in Peter's talk, this amazing experiment done by Andrew Lisko, computing nearest neighbor spacings at height 10 to the 20. And you see that the fit of this, this conjecture, which goes beyond RH to the two random matrix theory, is quite perfect. Now, as Peter also mentioned, Odlyzko studied many other things about the zeta function besides just the nearest neighbor spacings of the zeros. So in the same paper, you find other graphs which are maybe less compelling than the previous graph on the zero spacing. So this is a graph that shows the distribution of log mod zeta half plus IT. And this is the expected Gaussian. And you can see that what's happening even at 10 to the 12 or 10 to the 20, it doesn't look so close to being Gaussian. 10 to the 20 looks a little better than 10 to the 12, but not much better. So you could ask what's going on here. And also what's interesting about this is that this is actually data trying to data in support of a theorem, which is not very convincing, whereas data in support of a conjecture is much more convincing somehow. So this brings us to the insight that Keating and Snaith had in 1998, which is that perhaps not just the zeros of the zeta function, but also other properties of the zeta function could also be modeled at height t using random matrices. And the key new point is that you can say something about the size of the matrix. Instead of just saying t goes to infinity and n goes to infinity, you can try to make a relationship between n and t. And the way they arrived at this relationship was to say, well, the spacing between zeros at height t is about 2 pi over log t. The spacing between eigenvalues of an n by n matrix is about size 2 pi over n. So you might set those two spacings to be equal to each other, which suggests a relationship between n and t. So n might be on the scale of log t. So maybe the zeta function at height t looks like a random matrix of a particular size log t, rather than just large random matrices. And in this picture, the analog of the zeta function would be the zeta function has the zeros of the zeta function as its zeros. The characteristic polynomial of a random matrix has its eigenvalues as the zeros. And so maybe the analog would be the characteristic polynomial of the random matrix. So you could model the 10 to the 20th zero around that height by matrices of size about 42. Maybe 42 is a little bit of a fudge, but I think it's close enough to log of 10 to the 20. So then you have this, this amazing graph of Keating and Snaith. This is redoing the Odlyzko computation, but now for the distribution of log mod zeta. So you still have the Gaussian, and it's not near the Gaussian, but you have two graphs that are kind of almost superimposed on each other. The actual distribution for log mod zeta at height 10 to the 20, and also what the picture for matrices of size 42. So if you let the 42 go to infinity, you should get to the Gaussian. If you let the 10 to the 20 go to infinity, you should also get to the Gaussian. This seems more compelling. So I sent these slides, or a version of them, to Ben Green, who complained about my spelling of marvelous for Odlyzko, and said that at least for Keating and Snaith, I need to spell it the English way. So once you have this insight, you can then go back and make predictions for the moment. So instead of computing the moments for zeta, you could try to compute the analogous moments of characteristic polynomials of a random matrix. So it's a manifold integral, which you can write down. And amazingly, this integral can be transformed to an integral that was evaluated by Selberg. And you can compute exactly what this integral is. And then if you are interested in the asymptotics of this as n gets large, that's a simple calculation. And you get this, arrive at this constant gk, which I mentioned before. So this is what matches up with the 42 and the 24,024 and suggests what the constant should be in general. So in this conjecture of Keating and Snaith, you only guess what this constant gk is, and the ak doesn't appear at all. The product over primes doesn't appear at all, and it has to be put in by hand. So John mentioned that these come from what happens in examining the tail of these distributions of zeros, and so you could believe that these are some long-range correlations, maybe coming from primes, and you have to input them by hand rather than through random matrix theory. There's a way in which Gonek, Hughes, and Keating view this, which is also, I think, quite compelling, that you could view the zeta function as being given both by primes and as a product over zeros. And you could try to make a hybrid model where you take some number of primes and take some number of zeros. There should be some kind of uncertainty principle that the more primes you take, the fewer zeros you need to take, and the fewer primes you take, the more zeros you need to take. And then if you posit that the behavior on the primes is kind of independent on the behavior of the zeros, this would then suggest, once again, the Keating-Snaith conjectures for why you should get an AK times GK in the answer. Now, there's been much further work in this direction. So the Keating-Snaith conjecture applies for all real moments K rather than just integer moments. But for integer values of K, there's been other advances, a recipe of Connery, Farmer, Keating, Rubinstein, and Snaith, and a closely related method of multiple Dirichlet series developed by Diacono, Goldfeld, and Hofstein. You can write down much more precise asymptotic formulas. You can put in shifts as well. So you can put in K shifts, alpha 1 to alpha K, and K other shifts, half minus beta 1 minus IT to half minus beta K minus IT. You could then, if you let all the shifts go to 0, you would get just this 2kth moment of zeta. But you can, what they were able to do was to identify the entire polynomial. There's a polynomial pk of degree k squared, and you can identify all lower order terms in a conjectural asymptotic formula for moments, and maybe there's a power saving error term after this. I don't know if it's well accepted what the power saving should be. There should be maybe some power saving, maybe all the way up to t to the half, but it's not clear if that's so natural. So I've given you this polynomial of degree 9 for P3 for the 6th moment. The numbers are not very informative, but maybe the only thing to notice is that the leading coefficient is extremely small, whereas some other coefficient here is reasonably big. So you can see that a conjecture like this is important if one wants to understand numerically problems of this type, because just knowing the leading order in any range in which we are able to investigate, you're not going to be able to tell whether the conjecture is reasonable or not. Okay, so that's the story for Zeta. There's a similar story for values of L functions in families. So again, the connection between the distribution of zeros in these families and the distribution of the low-lying zeros in these families, that goes back to work of Rudnick and Sarnak, and then Katz and Sarnak. We heard about that in the morning already. And there's a similar, the same insight of Keating and Snaith would suggest that you can, again, model other properties of these L functions, like their central values, by studying the characteristic polynomial in these different families of random matrices. So I've given you two such examples to take the family of quadratic Dirichlet L functions, or the quadratic twists of a given modular form, and say restricting myself to twists where the sign of the functional equation is positive. If the sign of the functional equation is negative, then these values would just be 0. You could study in that case the derivative of these central values, if you like, by similar methods. So in this context, there's much that's not as well understood as for Zeta. So there's an analog of Selberg's theorem, but it's only a conjecture of Keating and Snaith, that if you take the logs of these values, these are all Gaussian. They're all real valued in this case, presumably never 0 or rarely 0 in this case. But there's a slight difference. So the mean value is positive and half log t in the case of quadratic Dirichlet L functions, and the variance is log d. And the mean value is negative in the case of quadratic twists of a modular form, and still log d with variance. So in other words, if you look at the raw values of L half chi d for quadratic Dirichlet L functions, those tend to be kind of big. Whereas if you look at the raw values of L half f twisted by chi d, those tend to be a little bit small, at least typically. So here's kind of a heuristic for why you might expect this. For Zeta, I just said, okay, you can think of taking the log of the Euler product, even though it doesn't converge. If I do something similar here, I want to take, so the log of it is a sum over all prime powers. I've written down the prime contribution and the prime square contributions. The prime cubes and prime to the fourths are all irrelevant because they're convergent. So that's just big O of 1. The prime contribution will be what's giving me a Gaussian. These would be plus minus 1 with equal probability. So this should go to a Gaussian. This also, these are plus minus 1 with equal probability, should go to some Gaussian, which we can evaluate. But what's different is the contribution of the squares. If I look at quadratic Dirichlet functions, these are all 1. So that gives me a half log x. And that's the mean that we see in this Keating-Snaith conjecture. And in the other case, if I look at twists of a modular form, so here the coefficients of the modular form I've written as AP alpha p plus beta p. So you get alpha p squared plus beta p squared, which is -1 on average. So alpha p plus beta p quantity squared is 1 on average, which makes alpha p squared plus beta p squared -1 on average, just from Rankin-Selberg theory. So the means are different, but they're still Gaussian. But as I've said, these are only conjectures. And the reason why these are conjectures is because for all we know, many of these values could simply be 0, in which case the distribution would not be what is stated. So for example, for quadratic Dirichlet functions, we know that 7/8 of the discriminants at least satisfy that the L values are non-zero, but it's not 100%, and the conjecture would imply that 100% of these values are non-zero. For twists of a modular form, we don't even know in general that a positive proportion of these L values are non-zero. So again, you can't hope to prove the analog of these of Selberg's theorem in these situations without making progress on these. You could also carry out the same computation that I did of taking the exponential moment of a normal random variable, and you would get analogs. So these conjectures were again made by Keating and Snaith. You can get analogous conjecture for moments of L functions in the kth moment of L functions in families. And you can see that this mean being positive or negative is kind of reflected in the exponent k times k minus 1/2 or k times k plus 1/2. So these are conjectures that you could make for all real values of k. And you can see if I formally let k go to 0, that will then pick out whether this value is 0 or non-zero. It'll be 1 if you're non-zero and 0 if you're 0. So understanding these moments as k goes to 0 is also the same problem as understanding the non-vanishing in these families. So those are the problems on this on connected to moments. Let me briefly say something about what progress has been made. So in many, many situations, we know lower bounds of the right order of magnitude. This started with work of Ramachandra and Heath Brown already in the early 80s, or maybe late 70s, for the Zeta function. And then I had worked with Zev Rudnick in families, and then also with Max. And the latest version of it is work with Heap, Winston Heap. And the principle we have for lower bounds is that if you know the first moment in any family of L functions, plus the ability to put in a small Dirichlet polynomial, which is what I mean by this plus epsilon, then you can get right lower bounds of the correct order of magnitude for all larger moments. So for example, for twists of a modular form, we only know the first moment, but with something to spare. So you can get the right lower bound for all larger moments in the first. For the Zeta function, we can get lower bounds for all real k, all positive k. We can get the lower bound of the right order of magnitude. And the same thing for, say, all moments of quadratic Dirichlet functions. These two cases are a little bit different than the case for modular forms. They also include low moments, which, as I said, is related to non-vanishing. So we are able to do low moments for Zeta and for L half chi d because we can compute two moments in this family, say the second and the fourth moment, or the first moment and the second moment in this case. And that's enough to get lower bounds for low moments as well, but not in the case of twists of a modular form. So this is maybe the one result that I'll try to give a little bit of an idea of the proof of, and I'll describe corresponding results for upper bounds and asymptotic formulas as well, just to state where the subject stands. So the idea in all of these proofs is that you should think about Euler product, but make computations using Dirichlet series. So here's what I mean. Suppose I could compute, let's not worry about what x is, think of it as a small power of t. Suppose I could compute zeta of half plus it, and then this is like log of zeta half plus it. So that's like zeta of half plus it to the k minus 1. That's zeta of half minus it to the k. So if I could compute this, that's basically the same as the 2kth moment of the zeta function. Let's imagine I can compute this. If I can compute this, then Holder's inequality would tell me that I can get a lower bound for the 2kth moment in terms of this Holder exponent would be a 2k over 2k minus 1, giving me again the same object here. So if I could compute this and I could compute that, then I have a lower bound for the 2kth moment of the zeta function. But now the trouble is that I can't compute any of these objects, because if I try to expand this out, I would get a Dirichlet series whose length would be extremely long, and I can't compute anything with using that Dirichlet series. I can't compute either this, or I can't also compute that. However, what you can use is that the sum over primes is not often very big. I can compute, for example, its variance. Its variance would be the sum of the reciprocals of the primes up to x. That's only log x. So most of the time, the sum over primes is not very big, not as big as log x. So let's imagine that you're in the usual case when it's not very big. This is a little bit of a lie, because the moments are actually capturing values of the zeta that are big. So the sum over primes is also likely to be big. So you should take this with a pinch of salt. But like if I pretend that the sum over primes is not very big, then what I could do is I could replace the exponential by its Taylor series approximation going up to some point beyond where I know that prime sum goes. Okay, so now this has the advantage that it really looks like the exponential, but in reality, it's a short Dirichlet polynomial. If I think of x as being a very small power of t, this is still a very, very short Dirichlet polynomial. And now I can compute everything I want. Well, at least I can compute the starting point. This is just the first moment with epsilon thrown in. That's what I mean here. If I use Holder, I'll have to compute some very unpleasant thing, some object. I'm looking at its LP norm when p is not an even integer. It's never going to be an easy problem. However, if I pretend that this is an exponential, if this is an exponential and that's an exponential, then this is basically the L2 norm of another exponential. And one can make this intuition precise by arguing that the sum over primes is not big most of the time. So that's a very brief overview of this proof. And really, we were motivated in this proof by sieve theory, which if you think about it, is doing very much the same kind of technique. In sieve theory, you want to understand whether numbers are divisible by a whole bunch of primes up to some point. So you have a function which you can think of as a product over primes p of 1 minus the delta function of p dividing your number. We can't do anything with that Euler product. So what we do is we expand out into its series, which will be the Möbius function times whether your number is divisible by some number d or not. And that we can understand so long as what we evaluate doesn't contain too many terms. And we are basically reproducing, in this context, the pure Bryn sieve, more or less. This will have some small imperfections, like I'll be off by a powers of log if I just carry this out, but you can iterate this, and then that gives you the lossless results, lower bounds that I described. So there's a similar principle for upper bounds. If I know some moment plus epsilon, then I can get upper bounds for all smaller moments. So This is not simply what Holder's inequality would give you, because this exponent here is quadratic. If it were linear, this would be a complete triviality. But since it's quadratic, you have to get the right exponent, you have to work a little bit harder to get there. So in particular, for example, the zeta function, we understand the correct order of magnitude of the zeta function for all real moments between the second moment and between 0 and 2. So now, tomorrow we'll hear a little bit more from Bailey on this theme, that you can refine this a little bit more and actually say, I mentioned that the 2 kth moments are connected to large deviations in Selberg's theorem. They're measuring the measure of the time on which you take values of size log t to the k. So this recent refinement of Argan and Bailey actually gives the right upper bound for the measure of large values of t in the same range that I've stated this moment. Actually, yeah, in the same range that we've stated. Now, on GRH, we can do much better. So we can get, if we know RH, we can get the right order of magnitude for all the moments of the zeta function. This is a result of Harper refining a result of mine. I had a result with k squared plus epsilon here, and Harper found an ingenious way to remove the plus epsilon in this result. The main idea behind these proofs is that I mentioned this, this hybrid model you could think of the zeta function as being given by both an Euler product and a product over, and a Hadamard product, a product over zeros. You can imagine that, that the zeros of the zeta function are making the zeta function get smaller rather than getting larger. So if you want to just get an upper bound for the zeta function, you can just upper bound it by a sum over primes with an error term, which is like an uncertainty principle. Again, the more primes you allow, the better your error term gets. But the flexibility in this bound is that you can choose x to be whatever you want. So for example, if you chose x to be like log x or log x squared, you would get the Lindelof hypothesis out of this. If you choose it to be log x, just bound this trivially, you still get log x over log t over log t as the bound for the zeta function. Now, once you have a result of this type, you can now study this. You can take moments of this if you like and understand enough about the sum over primes to get bounds on the moments. So this result, especially with the sharp refinement of Harper, has proved useful in many different contexts. So I mentioned 2 beautiful recent applications, one by Lester and Rajivi, who showed that if you take a half integer weight modular form, you can get a positive proportion of sign changes among its coefficients, conditional on GRH. And one of their inputs is this ability to get sharp bounds on these moments. And another recent application is by David, Florea, and Lalin. And they showed that if you take cubic Dirichlet L functions over the function field, where you know the Riemann hypothesis, so this is an unconditional theorem because we know GRH in this case, then you can get a positive proportion of these L values being non-zero at the central point. And this is interesting because people who've thought about non-vanishing would recognize that you want to use something like the mollifier method to understand this. But this is an example where we are not able to compute the second moment, but we can get the second moment with the mollifier thrown in. We can get an upper bound for that by techniques of this type. And that's enough for showing a positive proportion of non-vanishing. The other type of progress has been to get asymptotics in many special cases. So I give a few of these examples. Maybe I'll just say something about 2 of them, which we will hear from Pai Chandi on Friday, hopefully, that you can compute the 6th moment of all Dirichlet L functions with conductor going up to Q. So earlier, Conry, Ivanets, and I had done a version of this calculation where we had a little small integral like in the 8th moment here. but they were able to remove that imperfection and get the sixth moment just at the central value. And you can see the same constant 42 show up in the answer there. And they've also been able to evaluate the eighth moment with a little small integral here and recover the 24,024 that was conjectured for the eighth moment. Okay. So I have a few minutes more, and I want to say something about, oops, I had still more to say about the central limit theorem, that we have one-sided central limit theorems to this. Maybe I'll go through this quickly because I want to say end with a new connection to Gaussian multiplicative chaos and also to branching Brownian motion, which will be the theme of many lectures tomorrow. So this is a problem from maybe about 10 years back, started by Fyodorov, Hyary, and Keating, where they want to study the maximum of the zeta function in intervals of length 1 as you vary the interval on the critical line. This may look like a strange problem to study, except that if you think of it in random matrix theory, it's a much more natural problem. You pick a random matrix, and then you look at its characteristic polynomial, and you can ask, what is the maximum of the characteristic polynomial on the unit circle? That makes sense. And you can think that the zeta function in an interval of length 1, well, that's like one random matrix, so to speak. And so as you vary t, you're basically studying the problem of the maximum of the characteristic polynomial on the unit circle as your matrix varies. So what Fyodorov, Hyary, and Keating conjectured was that you have the distribution of this maximum. Well, if you remove the log, so the maximum of zeta is like log t, but it's divided by some power of log t. And what's important here is to focus on this constant 3/4 in red. It's not always going to be this. It's this plus some random variable, which is bounded almost surely. Now, what is the point of this conjecture? We know from Selberg's theorem that the logarithm of the zeta function looks like a Gaussian. So we could imagine that in an interval of length 1, you're taking maybe log t samples of independent samples of a Gaussian, and you can ask, if I pick log t independent samples of a Gaussian, what is the maximum among them? And that's a problem which I think the probabilists and the actuaries have been interested in for a long time, because it's a problem of, I guess, real world significance to understand the worst flood that can happen in 100 years and so on. And it was well understood what the maximum should be, but this constant in this in the lower order term is 1/4 instead of the 3/4 that's suggested in the conjecture of Fyodorov, Hyary, and Keating. So there's a good reason for this, and the reason is that if you take the log of two values of the zeta function that are close to each other, if you pretend that they behave like sums over primes, for the small primes, less than e to the 1/h, these values are more or less the same. And then for the large primes, they start behaving independently of each other or less correlated from each other. So the nearby values of zeta are correlated, and this is their covariance. And then as they move away from each other, they are more and more uncorrelated. And you have to take this covariance, this correlation structure into account. And one way to do this is not exactly the truth, but it's some kind of approximation to it. Imagine that you split the sum over primes into blocks from e to the k to e to the k plus 1. So this range is chosen, so the sum of the reciprocals of the primes in this block is 1 approximately. So you could imagine that the zeta function is a sum, the log of the zeta function is a sum of many of these objects, and each one of them is some kind of Gaussian with mean 0 and variance 1. Okay. Now, for the smallest primes don't change very quickly, but the largest primes will change much more rapidly. So the model is that of a branching random walk or branching Brownian motion, where you take, for the very smallest primes, maybe you have 3 different samples that you pick in your interval of length 1. Then for the next smallest primes, maybe you pick E squared, so about 7 different samples of the second sum, and then about let's say 20 samples of your third sum, and so on, and then you add all of these up in this branching way. And that gives a model for how the zeta function should look like. So here's a graph of, or some realization of what this branching process looks like. You have a particle that starts at 0, it evolves using Brownian motion, and then at some point of time, there's a chance that it'll split into 2 particles, which start from there and evolve independently with Brownian motion. And then at some point of time, each of those 2 particles will split into 2, and so on and so forth. So you get this cloud of particles at the end, and you would like to understand things like, what is the maximum of all of these particles? How large can it get, or how small can it get? And this turns out to be the story for zeta of half plus IT. And there's been a lot of progress on this by Harper and Argan, Bourgaard, and Rajivi. So we'll hear more about this from Louis Pierre's talk tomorrow. There are analogs of this in random matrix theory, which are also understood. In some cases, there's more progress. There's been more progress on the number theory side than in the random matrix theory side even. There are other related results of Harper on random multiplicative functions. Maybe Adam will talk about this tomorrow. I want to end by some work in progress with a couple of students of mine, Rodrigo Angelo and Max Xu, which has to do with a very concrete problem. Take a prime P, or you could take a fundamental discriminant chi-D, look at the character sums n over P of the Legendre symbol, and what's the chance that they are always positive? You would think that this is a very rare event. We were motivated by a beautiful paper of Kalminen from about last year on the archive, where he did numerics and he found that there are actually lots and lots of such examples. He found 1,000 primes below 55,000. So that's a reasonably large number of primes for which these partial sums are always positive. Earlier, Baker and Montgomery had shown that for almost all primes, this cannot happen. Kalminen improved their quantification a bit. But we've improved this further. And the observation is, if these partial sums are always positive, then you can write the Dirichlet L function. You can just write down the usual Mellin transform for the Dirichlet L function. This is the usual analytic continuation of L as chi. If these are all positive, then you can bound the L value at S by the L value at half, or sigma, if you say S is sigma plus IT, right? If this is positive, I don't have to take absolute values here. I just take absolute values there. That gives me X to the sigma plus 1. So in other words, this means that the central value L half chi is bigger than a constant times the maximum between 1 and 2. And this is the kind of problems that I've been talking about in the rest of the talk. We know how the central value L half chi D should behave. Typically, it's on the size of log X to the half. We know what the maximum of this should behave. It behaves like log X to the 1. So you see that this is an unlikely thing to happen. So by making this precise, we've been able to show that there are at most X over log X to the 1/8 such discriminants up to X. You could do corresponding results for prime moduli as well. But what is curious is that there do seem to be lots of these characters, even though we don't know that there are infinitely many such characters. If there were infinitely many such characters, you would know that there are no real zeros of quadratic Dirichlet L functions. Brian Conry and I showed that for a positive proportion of characters, but this would give you a different way of approaching problems of that type. And it may even be that there are X over square root of log X such characters, although, as I said, we can't even prove that there are infinitely many. So thank you very much.
Other questions? If not, then we are adjourned. So